Hi everyone, I am Dr. G. Srinivasu, Associate Professor, Department of Mathematics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In the present video, I would like to discuss the problems on Green's theorem. In the previous class, we have stated Green's theorem and we have seen some application problems on Green's theorem. So in this video also, I would like to present some more problems on Green's theorem. So what is the statement of the Green's theorem? So it is a transformation between line integral and double integral. Suppose if C is, let us explain, if C is any closed region bounded by a curve C and R be the region bounded by the closed circuit C, and it is x-axis and y-axis, and M and N are two functions, continuous and differentiable functions defined on this curve, then integral over the closed curve C, M dx plus N dy is equal to double integral over the region R, dou N by dou x minus dou M by dou y dx dy. So it is a relation between line integral and double integral. So C is the closed curve bounded by the region R and R is this region. So to find the line integral, we need to consider this curve, and to find the double integral, we need to consider this region. Double integral means you have to consider the strip inside the region, and you have to take the limits for y and x, and then integration is to be performed. So I will go to the statement also. Green's theorem in a plane, transformation between line integral and double integral. Let R be any closed region in xy plane bounded by a simple closed curve C, and if M and N are continuous derivatives in R, then integral over closed curve C M dx plus N dy is equal to double integral over R dou N by dou x minus dou M by dou y dx dy, where C is traversed in the positive direction. That means what? In anti-clockwise direction. C is moving in anti-clockwise direction. That is called in the positive direction. Anti-clockwise means positive direction. So we have to consider the line integral along this direction. So that is an important point to be noted. So double integral, already we know that we have seen many problems on double integrals. So based on that, we find the verification, we can solve the verification problems of Green's theorem, as well as we can find some value using one is given, right? So we'll see the problems on Green's theorem. Verify Green's theorem in a plane for the function integral M dx plus N dy over the closed curve C, where C is the region bounded by y is equal to x and y is equal to x square. So what is the curve y is equal to x, y is equal to x square? The curves y is equal to x and y is equal to x square. So it is a straight line passing through origin. It is in the form y is equal to mx notation. And this is y is equal to x square means it is a parabola symmetrical about y axis. This is y is equal to x square parabola. So it should be in a symmetrical way. I will write one more here. It is 0, 0. This is x-axis. This is y-axis. This curve is y is equal to x square. And other one is a straight line passing through origin. Y is equal to x line. This is y is equal to x line. Now the curve is like this. The curve is like this. The curve, suppose if it is O0, 0, and the points, these points of intersection on solving the two equations. On solving two equations, y is x and y is x square. So x is equal to x square. So x minus or x square minus x is equal to 0, or x into x minus 1, 0. So the values of x are 0, 1. So y also 0, 1. That means what? 0, 0 is 1 point. Already we know that It is the vertex. And other point is 1, 1. So now we have to evaluate the line integral along OA and along AO, because it is the positive direction OA and AO. OA means from 0, 0 to 1, 1, and AO means from 1, 1 to 0, 0. That is to be evaluated in the line integral case. In the double integral case, we have to consider this region is capital R. This is the region capital R. That will be explained later. Now, we know that by Green's theorem in a plane, what we have? Integral over the closed curve C, mdx plus ndy is equal to double integral over R, dou m by dou x minus dou m by dou y of dx dy. So that is the formula by using the Green's theorem. That is the statement of the Green's theorem. The line integral relation to the double integral. So here the line integral already given that in the problem, integral mdx plus ndy already given in the statement, integral xy plus y square dx. I will write here, given integral over the closed curve C, xy plus y square dx plus x square dy. So it is given already. So already given that it is the given function, and we have to verify the Green's theorem. Here what is the notation? Mdx plus ndy. So what is m? It is xy plus y square, and n is equal to x square. So I will check the values once again. X square dy, xy plus y square, xy plus y square. Then what is dou m by dou y? The partial derivative of m with respect to y. So this is x into y1, and it is 2y. That is x plus 2y. And similarly, dou n by dou x, that is equal to 2x only. Now, consider double integral dou n by dou x minus dou m by dou y dx dy over the region R. I am considering RHS term. First I would like to evaluate the right hand side term, that is integral double integral over R. Dou n by dou x is 2x minus dou m by dou y. What is dou m by dou y? Minus x minus 2y, and this is dx dy. So what is the value? X minus 2y, that is double integral x minus 2y dy dx over the region R. So now we have to find the limits of integration. How to find the limits of the integration? One is parabola. This parabola is given as y is equal to x square, and other one is a straight line y is equal to x, and I am assuming this is the region R. I am considering the strip inside the region. On taking the strip inside the region, and this is 1, 1, and this is 0, 0. So the lower edges of the strip is on y is equal to x square. The strip lower edge is on the curve y is equal to x square. So the lower limit for y is x square and upper limit is x. And x limit is 0 to 1. So therefore here x varies from 0 to 1 and y varies from x square to x. Y varies from x square to x. Therefore, double integral over the region R, x minus 2y dy dx is equal to, so what is the evaluation? Y x square to x. So the integration, you know the procedure of performing the integration. We have to perform the integration of the given function with respect to variable limit first, then with respect to the constant limit x 0 to 1, the function x minus 2y dy first, then finally with respect to dx. You know, as per the procedure of the evaluation of double integrals. Now integral 0 to 1. So what is the integration? Xy 2 into y square by 2 with respect to y, and lower limit x square, upper limit x of dx. So this is equal to integral 0 to 1. So what is the upper limit? Instead of y, if you replace x, it is x square. So instead of y, I am writing x square minus x cube, replace y for x square, x cube, plus x power 4 of dx. I am replacing y for x square whole square, x power 4. So these two gets cancelled, and this value is integral x power 4 minus x cube dx between 0 and 1. So what is the integration? X power 4, x power 5 by 5 minus x cube integration x power 4 by 4 between 0 and 1. That is 1 by 5 minus 1 by 4. The LCM 20, 4 minus 5, that is equal to minus 1 by 20. This is the RHS value. The integral value with respect to the double integral. Right hand side value of the Green's theorem. So what is the value? Minus 1 by 20. This is integral function dou n by dou y minus dou n by dou x minus dou m by dou y of dx dy. So that is the function. So similarly, we calculate the line integral. What is the line integral? I will show integral. This you have to calculate. xy plus y square. Now consider LHS. Integral over the closed curve C, xy plus x square. Am I right? xy plus y square. Sorry, xy plus y square dx plus what is the other one? X square dy. We have to evaluate the line integral along the closed curve. What is the closed curve? So one is the parabola and other one is a straight line along OA. So I have to write this is integral along OA plus along AO. So what is case 1? So I am studying case 1 along OA. This is 0, 0 and this is 1, 1. 0, 0, 1, 1. Along OA means what is this curve? This curve is y is equal to x square and this curve is y is equal to x. So along OA means along the curve y is equal to x square. Am I right? This is the part of the curve y is equal to x square. So y is equal to x square means what? Dy is equal to 2x dx. Dy is equal to 2x dx. And here x varies from 0 to 1. So integral x varies from 0 to 1. X into y means x square. I am replacing y for x square. Dy means this is. Plus y means x square means x power 4 dx plus x square as it is dy 2x dx. That is the first integral along OA, then along AO. So here x varies from 0 to 1. Am I right? That's why I have written here the function, entire function changed into function of x, that is 0 to 1. It is x power 4 x cube plus 2x cube. That is what? 3x cube plus x power 4 of dx. See this is x cube. Already here 2x cube is there. 2x cube plus x cube, 3x cube plus x power 4 dx is common term. Now on integrating 3x power 4 by 4 plus x power 5 by 5, the limits are between 0 and 1. So I'm substituting the limits 3 by 4 plus 1 by 5, lower limits both are zeros. So LCM 20, 4 5s, 5 3s 15. 5 4s 20, that is equal to 19 by 20. That is the first integral value along OA. Similarly, we have to evaluate along AO also. Along AO. So that will write in the next slide. That is case 2. Case 2, or I can use this case 2. I can write here also. Case 2 means along AO. Along AO means along y is equal to x line. Am I right? Along y is equal to x line. This is the figure you need to consider. This is A1, 1, 2, 0, 0. Along AO you have to calculate. Along AO. Along AO, what is the line? Here y is equal to x, then dy is equal to dx. So integral along AO m dx plus n dy is equal to integral, and here x varies from 1 to 0. X varies from 1 to 0, and replace y for x. Y for x means x square plus x square dx. Y plus x, that is x square. Here we replace y for x, that is x square dx as it is, plus x square as it is, dy is equal to dx. So then what is the value? Integral 1 to 0 x power 4, sorry. So what this is, x square plus x square plus x square, that is 3x square dx, or 3x cubed by 3 between 1 and 0. That is 3 cancel, the value 0 minus 1, that is equal to minus 1. So what is the first value? Therefore, integral along the closed curve C, this is equal to, the first value we got minus, I will show this. What is the value? Some 19 by 20, I think. Minus 1 by 20, second value. 19 by 20. This is the first value, 19 by 20 along AO. Along OA it is 19 by 20. And along AO this value is equal to minus 1. So this is 19 minus 20 by 20, that is minus 1 by 20. Second value. Second value means LHS, that is a line integral along the closed curve C is minus 1 by 20. Call this is equation number 2. Now see the equations 1 and 2. The second value minus 1 by 20. And first also we got minus 1 by 20. That means what? The LHS is equal to RHS. So our Green's theorem verified. That is the required solution. Green's theorem verified. So just you need to consider the closed curve, and you have to evaluate the line integral along the closed curve C. In the similar way, you find the region R and find the double integral in that region R. So that will be minus 1 by 20 in both the cases. So the Green's theorem is verified. That is the required solution of the given problem. I hope already we have done 3-4 problems, so we can do easily. And we go for one more problem. So here that is not verification problem. Apply Green's theorem in a plane. So we go for the problem number 2. Apply Green's theorem in a plane to evaluate integral m dx plus n dy, where m is 2x square minus y square, n is x square plus y square, where C is the boundary of the area enclosed by the x-axis and upper half of the circle. So you know the circle equation, x square plus y square is equal to a square. This is a circle equation. I will draw once again because it is the circle equation whose center is 0, 0 and radius is equal to a units. It is a circle equation. So this is x square plus y square is equal to a square. Where C is the boundary of the area enclosed by the x-axis and upper half of the circle. Only semicircle. The region is only the semicircle only, not full circle. So this is the region. So to evaluate this line integral, we are supposed to apply Green's theorem as per the given problem. So here, what is M? So here we know that by Green's theorem, what we know that integral over closed curve C. This is also closed curve. You can find this is also closed curve. Integral over C m dx plus n dy is equal to double integral over R dou n by dou x minus dou m by dou y dx dy. So this is the statement of the Green's theorem, and it is a relation between line integral and double integral. So here we have to evaluate the line integral using double integration. That means applying application of Green's theorem. So here what is m? That means first you need to find these two values, dou m by dou x, dou m by dou y. What is m here? Here m is 2x square minus y square, and n is equal to x square plus y square. Then what is dou m by dou y? The partial derivative of m with respect to y. So that is minus 2y only. First term will be 0 because we are integrating with differentiating partially with respect to y. And what is the second one? Dou n by dou x. This is 2x only. Now dou n by dou x minus dou m by dou y is equal to 2x minus of minus 2y, that is 2 into x plus y. Now what are the limits of integration? Here now I will go to the next slide. Now integral, now by Green's theorem, integral over the closed curve C m dx plus n dy is equal to double integral over R dou n by dou x minus dou m by dou y dx dy. That is double integral over R. So this is x plus y into 2 dx into dy. 2 into x plus y dx dy. So what is the region R? Here R is the region of the semicircle. So this is 0, 0. We can consider this is radius is equal to a, and we can go for the transformation. We can convert the given double integral into polar coordinates. So polar coordinate means that will be easy. Theta 0 to pi. Here theta, suppose if you convert the equations into polar coordinates, we have to take x is equal to, what we have to take? X is equal to r cos theta and y is equal to r sin theta. Then what is x plus y? R into cos theta plus sin theta. And dx dy is equal to r dr d theta. Theta varies from 0 to pi. Theta is varies. This is theta 0 line. This is theta pi by 2. This is theta is equal to pi line. So only the upper part of the x-axis. So theta 0 to pi only. But r is varies from 0 to a. R is a strip considered from the pole. Here r0. This is r is equal to a. So the strip is to be considered from 0 to a. So r value 0 to a and theta values from 0 to pi to constant x plus y r into cos theta plus sin theta into again dx dy means r dr d theta. So the entire function in Cartesian system in xy terms change to r and theta terms, because evaluation of the integral in the polar coordinates will be easy when compared to the x and y. So 2 into 0 to pi theta limit, and this is 0 to a r square cos theta plus sin theta. So this is r limit, this is theta limit. You can do the integration according to your convenience. First dr, then d theta, because all the limits are constant limits. So you can perform the integration according to your convenience. You can do first integration with respect to r and then theta, or first theta and then r. You can perform in any order. There is no restriction on the integration. So first I am doing the integration with respect to r. So r cube by 3 and 0 to pi and cos theta plus sin theta remains same into d theta. So just you see here r square integration r cube by 3. So 0 to a. So r limits are 0 to a only, not 0 to pi. Theta limits 0 to pi and cos theta plus sin theta treating as constant term because we are integrating with respect to r d theta. So this is 2 into, and substituting the limits, upper limit a cube by 3, lower limit 0. So this I can write 2a cube by 3 integral 0 to pi cos theta plus sin theta of d theta. I hope this is clear. The integration is very easy when the conversion done into the polar form. Otherwise, you can consider in xy also, but y limits varies from 0 to square root of a square minus y square, like that. Is a little bit complicated in evaluating the double integral. In that also you can do that, no problem, according to your wish. So cos theta integration, that is sin theta, and sin theta integration minus cos theta 0 to pi. So 2a cube by 3 sin pi 0, cos pi minus 1. Cos pi means I can write it is cos pi upper limit minus 1, lower limit sin 0 0 plus cos 0 1. So this is equal to minus of minus plus 1, 2a cube by 3 into 2. That is equal to 4a cube by 3 is the required double integral value, and which is integral over the closed curve C m dx plus n dy. So this is the solution of the problem. The answer is 4a cube by 3. That is the required solution of the given problem on applying the Green's theorem in a plane. So in that way you can evaluate the double integral or line integral according to the Green's theorem in a plane, and you can verify the problems also using Green's theorem. So these two are the two examples we have discussed in the session. And we see some example, and it is used as a practice problem. I will explain and you work out at your own. And here also we have to verify Green's theorem in a plane. Already you know that the Green's theorem is integral over the closed curve C m dx plus n dy is equal to double integral over R dou n by dou x minus dou m by dou y dx dy. Here m is there, n is there. You can calculate dou n by dou x, dou m by dou y, and dx dy. So you can do the double integration. Only thing is finding of the limits. So that I will explain now itself. You do at your own. And here in the left hand side you have to evaluate the line integral along the curve. What is the curve? C is the square with vertices. So given C is a square with vertices 0 0 is one curve, and 1 0 2 0, this is one point. See, 0 0 is one point, oh, let it be, and a 2 comma 0 is the other point, and 2 comma 2 means this is the point 2 comma 2, so this is the point B, and other vertex C is 0 comma 2. So these are the 4 points to consider as the limits, and the limits of integration I will tell you. The direction will be positive direction. That means you have to find along OA plus along AB plus along BC plus along CO. You need to calculate the 4 different integrals. Integral along OA, integral along AB, along BC, along CO. So that will complete the evaluation of line integral. So I will explain this also. Along, this is x-axis and this is y-axis. Suppose if we want along OA. So what is the equation of OA? X-axis equation means y is equal to 0. So dy 0. dy 0 means what? Second integral value. This term will be 0. And y 0 means this also 0. Only you will get integral x square dx. And x varies from 0 to 2. So these are the limits. The value x cube by 3. 0 to 2, that is 8 by 3 is the first value. Very simple to evaluate. So you see one model along OA. Along OA means the equation is x-axis, so this is y is equal to 0. So y 0 I am putting dy 0, but x is a variable, x varies from 0 to 2. So that I am substituting here integral 0 to 2, y 0 dy 0 means entire term 0. And here y 0, that means x square only the term on the right hand side, x square dx, that is x cube by 3, 0 to 2, so 2 cube and 8 by 3, lower limit 0. That is the first value of the line integral along OA. Similarly, along AB also you can find, this is the equation, x is equal to 2. Second equation, x is equal to 2 means dx is equal to 0. and y varies from 0 to 2. In that way, you calculate the a along AB along BC along CO. Similarly, you find the double integral also. Already dou n by dou x, dou m by dou y, you can find dx dy, and you find y limits x limit by taking the strip inside the region. So on x-axis y0 to, this is y is equal to 2, y0 to 2, and x also varies from 0 to 2. X also from 0 to 2. That gives entire square of the given problem, and this is the function dx dy. So you evaluate line integral as well as double integral and show that this is equal to this one. Then the Green's theorem will be verified. Automatically it will be verified, just you have to observe. So this is a closed curve and we are taking the line integrals along the positive direction, along anti-clockwise direction. Similarly, you find the double integral by taking the strip inside the region. So then you evaluate the integral, double integral value. So and observe that whether 1 and 2 are equal or not. If 1 and 2 are equal, that verifies Green's theorem. So automatically will be done. So in this way you can solve the problems in Green's theorem. So in the next video I will start the Stokes theorem in vector integration. So this completes our session. These problems are taken from Mathematical Methods book by S. Chand, 2006 publishers. So this is for your reference only. And thank you.
Like, share and subscribe. Hit the bell icon for more updates.